Welcome to our notes on applications of solving triangles. Students will be able to solve real-world problems applying the most appropriate method to solve a triangle, either the law of sines, the law of cosines, right triangle trig, special right triangles, and or the Pythagorean theorem. Number 1. A pilot has just started on the glide path for landing at an airport with a runway length of 900 feet. The angles of depression from the plane to the ends of the runway are 17.5 degrees and 18.8 degrees. So part A says label the diagram. The figure is definitely not drawn to scale, but we're going to let the line segment AB represent the runway. So in order for me to label this clearly and all at once, I'm actually going to read all the parts that I have to answer for this so I can make sense of the whole problem. So part B is asking me to find the air distance the plane must travel until touching down on the near end of the runway. So I'm going to need to find the air distance, so I need to understand where that is on the diagram. I also need to know where the near end of the runway is, and I'll find that out soon. Part C says I need to find the ground distance that the plane must travel until touching down on the near end of the runway. And part D says I need to find the altitude of the plane when the pilot begins descending. So I'm going to need to know where all of those things are on this diagram in order to make sense of what's happening. So first I'm going to talk about these angles of depression. An angle of depression is made from the horizontal where the plane is. So the first angle of depression is the smaller angle, 17.5 degrees. So that's from here to here, 17.5 degrees. And then the bigger one from the horizontal to this one, right here, is 18.8 degrees. Now, it also says that the runway length is 900 feet, and my runway is the line segment AB. So before I do this, I see that I'm labeling points like this A and that one B. So I'm just going to call this one C for familiarity. So I'm going to name that one C. So little c in this case is going to be 900 feet. So this is all we could label from the description, but now we're going to use our geometry knowledge to label other things as well. So first, let's recap some things that we're going to need to know from geometry. So here is a very, very simplified diagram of the airplane problem. And we're going to need to know quite a few things. We're going to need to know about alternate interior angles. We're going to have to remember that they are congruent. So I'm actually going to label two alternate interior angles of the red line, the transversal that goes through the parallel lines. So this angle right here from the top horizontal line to the red line and this angle right here are going to be congruent because they're alternate interior angles. We're also going to need to know about supplementary angles, so I'll use a different color here. Let's see, I'll use purple. So for supplementary angles, that's two angles that will add up to 180 degrees. So these two angles, this blue one down here and this purple one, are going to add up to 180, so they are supplementary angles. So because we are studying triangles, I think the triangle sum theorem is a safe one to always remember, that all angles of a triangle add up to 180 degrees. Now we're also going to need to know this one, the angle addition postulate. It's more straightforward than it sounds, but we're just going to go ahead and recap what that means. So this angle plus that angle makes up the entire angle. So that's all that means. So I'm going to write the measurement of angle ABC plus the measurement of angle CBD equals the measurement of angle ABD. Here, I'll move that down. So that's all that means, and we're actually going to use that on this airplane problem. All right, so let's figure out using the angle addition postulate, what this small angle is up here. So I know that this angle that I'm trying to find plus 17.5 degrees is going to equal 18.8 degrees. So using simple subtraction, 18.8 minus 17.5, I get 1.3 degrees. Now, let's look at what these transversals look like. There's three dotted lines. I'm not looking at the horizontal one at all. But I know in part B, I'm asked to find the air distance. Well, what is the air distance in this picture? The air distance is the distance that the airplane is actually going to travel. So the airplane is actually going to take this trajectory because it's going to touch on the near end of the runway. So point A is the near end of the runway, and so B is the far end, if that helps. So, the plane has to land, and once it lands, because it's going so fast, it needs time to slow down, and that's what it's going to do on that 900 feet of runway. So now if we focus only on this transversal line that's highlighted in yellow, then I'm going to use the alternate interior angle theorem to say that this angle must be 18.8 degrees. Now we can use supplementary angles to figure out what this angle is, this obtuse angle A. So I have the acute angle A, which is 18.8 degrees, but the obtuse angle A is going to be 180 minus 18.8. That will give me 161.2 degrees. All right, and now if I use the triangle sum theorem for this obtuse triangle here, 180 minus 1.3 minus 161.2 will give me this angle down here of 17.5. And look, I could have also used alternate interior angles to figure this one out because it is another transversal, and if this is 17.5 degrees, then this other angle down here has to be 17.5 degrees. All right, so let's not forget that part C is asking us about ground distance that the airplane has to travel in order to reach the near end of the runway, as well as the altitude of the plane, like right when it starts to descend. So what I'm going to do is I'm going to drop a perpendicular here, and I'm going to label this point D. And that ground distance, I think, what color did we name that one? Green. So that ground distance is going to be this part right here. So we're going to need to find what that green distance is. And the altitude, I think that was pink. The altitude, I'm going to need to find this one. All right, so I think we labeled enough of this to get started. So part B says find the air distance the plane must travel until touching down on the near end of the runway. So my hint to you is to draw a separate diagram of this triangle that you're trying to solve for. There's a lot of information in this diagram of the airplane. So simplifying what you see can help you figure out what you need to use. So I don't have enough information for all of these triangles, but the one triangle I do have enough information for is triangle ABC. So I'm going to redraw that. And since triangle ABC contains the air distance that I'm looking for, that's quite desirable to use. So here we have it. Okay, definitely not drawn to scale, but that doesn't matter as long as you label everything. An obtuse angle should look obtuse as much as possible, that kind of stuff. So this angle C from that diagram above is going to be 1.3 degrees. This angle down here, this obtuse one, is going to be 161.2 degrees. And this angle B is going to be 17.5 degrees. I know that the runway is 900 feet. That's our little C here. And I'll just relabel it or re-highlight it. That's what I'm looking for. I'm looking for that air distance. So I'm looking for little b. I want to know what this one is. All right, so I have all three angles of a triangle and I have one of the sides. So I can use the law of sines here because I have an angle and the side opposite it. So I have angle C and little c. Um, so I can just use the law of sines. So I'm going to need this ratio here. So little b over sine of big B equals little c over sine of big C. I'm going to solve for b. B is going to be little c sine b all over sine of big C. Now I'm going to plug everything in. 900 sine of 17.5 degrees divided by sine of 1.3 degrees. And that's going to give me That's going to give me 11,928.9 feet. So that is going to be the air distance. So I'm just going to write this in a complete sentence. The air distance the plane must travel until touching down on the near end of the runway is 11,928.9 feet. Part C says, find the ground distance the plane must travel until touching down the near end of the runway. So now I have a different triangle I'm looking at, and I have this right triangle here. Let's go back to the picture. I have the right triangle ADC, or CDA, however you want to name that. I need to know what that green distance is. I need to know what line segment DA is. And now that I know what the air distance is, I can use this triangle to figure that information out. So let me just recopy what I see here. CDA. Okay. So I have this right triangle here. Now, I'm going to call this C2 and A2 because that's going to be kind of different. The angles of these two points are going to be different. The angle A that I used in part B was the obtuse angle, and now I'm using the acute angle here. So I'm going to just label that A2. I don't know if I need to find C2, but let me see. I know this distance now. This one is 11928.9. Let me just double check. Yeah, so I know this distance from part B, and I'm trying to find this side, little c2. So I don't really have to find big c2. I can actually just use right triangle trig here. And C2 relative to the hypotenuse and the angle is going to be the adjacent side. So I'm going to use cosine. So I know that cosine of A2 is going to equal little c2, I'm trying to find, and the hypotenuse, which is this big number right here. So I'm going to solve for C2. So C2 is going to be equal to the hypotenuse times cosine, and I'll just write what A2 is, 18.8 degrees. That is approximately 11,292.5 feet. So the ground distance the plane must travel until touching down on the near end of the runway is 11,292.5 feet. Now it says find the altitude of the plane when the pilot begins descending. So I think this is going to be the same diagram as the one I drew above. I just know a little bit more information now. So I'm just going to go ahead and redraw. I now know that this is this much. I'm trying to find little a2 right here. So again, I can use right triangle trig to figure this out. I can use sine this time. So I know that sine of big A2 equals little a2 over the hypotenuse. Okay, so I'm just going to solve for a2. Okay, when I do that, I get 3,844.3 feet. So the altitude of the plane when the pilot begins descending is 3,844.3 feet. So that was the first airplane problem. That was the more complex one. For number 2, it's a little less complex. You try this one and then we'll go over it in class. Suppose 2 radar stations located 20 miles apart each detect an aircraft between them. The angle of elevation measured by the first station is 35 degrees, whereas the angle of elevation measured by the second station is 15 degrees. Find the height of the aircraft. So the picture is already drawn and pretty much labeled for you. You're going to have to find that dotted line right here. So you need to find this. Use what you know about law of sines, law of cosines, or even right triangle trig to help you answer this question.